Okay, hello. Section 23.3 is on lipids. Lipids means fats, although it sort of includes some things that you might readily recognize as fats and oils and some other things that maybe seem to surprise you. We're going to look at 4 different types of lipids. They're going to be triglycerides, phospholipids, steroids, and then prostaglandins. And those are the 4 lipids that we're going to investigate. So let me just pull up the slideshow again. I can't draw anything that is going to be helpful to you. And so we'll just look at the slides provided by the textbook publisher. So the first are triglycerides. So triglycerides are synthesized from a glycerol molecule. Glycerol is a propane molecule with an OH group on each of its 3 carbons, and so it could be called 1,2,3 propantriol, or you can call it glycerol. And these OH groups are able to perform condensation reactions with carboxylic acids to form ester linkages. And that's just what happens. So you'll notice the 3 fatty acids, and we'll talk about what makes a fatty acid in a minute, but you'll notice they all have a carboxylic acid on one end. And so those 3 carboxylic acid groups will form 3 ester linkages to the glycerol molecule, and you get a triglyceride. In this case, we have 3 different fatty acids. You can mix and match, have some that are the same and some that are different. Some of them will have double bonds and some of them won't, and that gives triglycerides a great diversity when you consider all the different combinations that can occur. So let's look at a fatty acid. This is palmitic acid, which I believe is named because it's isolated from like palm trees and oils that come from palm trees. And there's 3 different ways to write this, and honestly, most textbooks would have introduced this last method to you a little bit earlier, but that's fine. So up at the top is just the condensed structure, where we don't show any individual bonds, but we do show every carbon explicitly. And then down below that, we kind of shorten things, make our lives a little easier by saying, well, we've got 14 CH2s rather than write it 14 times. I'll just put them in parentheses with a 14 because these fatty acids tend to be long molecules. But down at the bottom is really the way that moving forward you're going to be drawing organic molecules. And so this looks like a zigzaggy line. Every end or vertex should be considered a carbon atom with as many hydrogens as it needs to form a total of 4 bonds. And so you'll notice that on the carboxylic acid end, instead of just having a line that ends like on the other end, you write an OH. So that's not a carbon, that's an oxygen and an OH. But every other corner or end of a line is going to be a carbon together with its hydrogens. And hopefully you can see the advantage to drawing molecules this way. We're able to actually convey structure and shape without giving ourselves carpal tunnel syndrome for writing so many H's and lines and things. So so these are different ways to represent that fatty acid, palmitic acid. So what makes it a fatty acid? Well, it's an acid because on one end it has that carboxylic acid group. That hydrogen on the end there, the OH, it really is acidic. If you were to take palmitic acid and stick it in water, well, it probably wouldn't dissolve very well, but to whatever extent it might dissolve, it will also change the pH a little bit. But more importantly, it's able to engage in acid-base reactions, sort of whether or not it dissolves in water. And one of those types of reactions is the ester bond formation, that that OH being labile or able to leave the molecule. So anyway, so that's why it's an acid. Well, it's a fatty acid because unlike something like acetic acid or formic acid, where the carboxylic acid group dominates the physical and chemical properties of the molecule, well, here we've got so many other carbons and hydrogens that they become very significant. All of those CH2 groups are going to create a long tail to this molecule that is nonpolar. It's going to be hydrophobic, which means it doesn't dissolve in water, that's gonna affect the way that fatty acids will behave. So anyway, here's an example of a couple of different fatty acids. The one on the left has, these are triglycerides, fatty acids that have been linked to a glycerol molecule through ester bonds. So the triglyceride on the left has all single bonds, and so this is called a saturated fatty acid. There couldn't be any more hydrogens added to this molecule, so it is saturated. And it's because all of the bonds in its three fatty acid tails are single bonds, there is a degree of free rotation, and they're probably going to utilize that free rotation to line themselves up. This is through what's usually called a hydrophobic interaction, but they'll probably line themselves up neatly and straight, and that's going to be important to its properties that we'll talk about in a minute. On the right side, you've got a triglyceride that has a double bond in each of its three tails. And those double bonds are rigid. They're rigid and they're bent. And so that's going to introduce these kinks in the way that those tails land. And the way that they physically land is going to affect its properties. So it's going to make it harder for them to pack together. It's going to reduce the surface area that's presented to their neighbors because they've got these jagged edges. And ultimately that's going to affect their melting points. So here we've got a number of natural oils and fats, and we'll typically distinguish between those, like say in a kitchen in a regular everyday sense. The difference between an oil and a fat is that the fat is solid at room temperature, the oil is liquid at room temperature. But they're actually all triglycerides, and there's a continuum. You know, something like margarine is kind of a solid at room temperature. Some butters are harder than margarine. Something like coconut oil is called an oil, but it's really very soft. Anyway. And so if you look at this table here, table 23.4, you can see that the higher the degree of unsaturation, as a rule, the higher the melting point is going to be. So if you have, and all of these natural oils are a mixture of many different types of triglycerides. That's why we can talk about their saturated and unsaturated percentages, because they're really a complex mixture of many different triglycerides. But something like olive oil is almost entirely unsaturated, 86% unsaturated fatty acids, and it's going to have a melting point, you know, well below freezing. And so that is because all of those kinks and bends and sharp corners prevent it from making good surface area contact with its neighbors, and so they don't stick together very well. Those molecules aren't able to really stick together. If you took me for 1210, you would have, or was that this class? Anyway, you would have remembered the analogy of Velcro. Velcro can be a very weak interaction, like if you have a tennis ball striking one of those little Velcro glove things. They look like loads of fun, but really the tennis ball bounces off half the time because that rounded surface prevents such a small area of contact, as opposed to, say, those places where you can put a Velcro suit on your body and jump spread eagle against a Velcro wall off of a trampoline. Well, in that case, even though you're so much heavier than the tennis ball, you're more likely to stick because you spread yourself out and present so much surface area to the Velcro wall. On the other hand, if you tried to ball up and like cannonball against the Velcro wall or give it your elbow or something, then it's not going to hold. So surface area is the most important factor here in how strongly attracted these molecules are to each other, and therefore how high their melting point is. More saturated mixtures are going to have lower melting points, and less saturation is going to have lower melting points for unsaturated triglycerides, high melting points for saturated triglycerides. So butter there isn't going to melt until you're well above room temperature. Now, because of that, the food industry has this practice of taking the oils and the fats that are part of their recipes and trying to dial in the right texture for their recipe. Usually what this means is taking natural oils and trying to saturate them in order to make them a little bit more solid at room temperature. If you think about margarine, for example, as a non-animal product, before the invention of margarine, then actual dairy butter was the only thing that you could really spread on your bread. A lot of people, I guess primarily in other parts of the world from America, at least where I grew up, people would dip bread in olive oil because that was the non-butter alternative. Well, margarine came in and said, well, now we've got a non-dairy product that is still solid like butter, and what they did is took these natural vegetable oils and they hydrogenated them. They added hydrogen and they converted some of those unsaturated triglycerides into saturated ones. Okay, so that's a fine process. But the problem is natural unsaturated triglycerides are always going to be in the cis configuration around that double bond. You see that on the left side. The two different branches go on the same side of that double bond. And I don't know exactly why, but that's how the enzymes that produce triglycerides within organisms do it in that cis configuration. And our metabolic processes, which will digest our food, are optimized to break down triglycerides that have their double bonds in the cis conformation. So trans fats, or fats that are double bonded but in the trans conformation, are problematic for our body. You've probably heard that trans fats are bad, and I don't know exactly why they're bad, except that to say that because they are not naturally occurring, our metabolic processes are not optimized to deal with them. And I guess someone that knows more than me can tell you more than that. The problem is, in the process of hydrogenating these unsaturated triglycerides, some fraction of them will remain unsaturated, but they will have transformed from the cis to the trans conformation. So that's where we get trans fats from. They are a byproduct of trying to saturate those natural oils to make them more solid at room temperature. Anyway, so that's where trans fats come from, and a really poor explanation for why they're bad for us. But the chemistry is solid. Basically, the reaction is going to sort of break that cis double bond and try to bind two new hydrogens to either side of it. Well, every now and again, the bond reforms after the molecule has done a little twist, and it will now be in the trans conformation. It doesn't quite make it all the way to being saturated, and it remains in the trans conformation. Okay, so that, is triglycerides. Now, we also have phospholipids, and phospholipids are actually really close cousins to triglycerides. If you look here, you see you've got the glycerol, you've got two fatty acid tails, just like a triglyceride, but the third position, instead of forming an ester bond to another fatty acid, is going to have this organic phosphate. So that's a PO4 3- ion that has been now incorporated into the structure of the phospholipid. And then, so the other side of the phosphate then will bind to some other group. In this case, it's a choline, but there's, again, a whole zoo of various phospholipids with different fatty acids and different groups on the other side of the phosphate. And what's really notable here is that the phosphate itself and then also that choline group on the top, they are charged. And so that makes the phospholipid break apart, it makes the phospholipid have two very distinct parts. The non-polar tail and then that polar head. It's not only polar, but it actually has full charges, and so that's going to form lots of really strong attractive interactions with other polar molecules like water. Essentially, a phospholipid is water soluble on one end, but it's water insoluble on the other end. And that's what makes phospholipids do what they do in the body. They'll form these bilayers that make up the membranes of cells and of cell organelles. So you'll have in the cell, you've got water on the outside of the cell and water on the inside of the cell. But you want to have a separation between those because the cell maybe wants to store lots of proteins and enzymes and sugars within its own cell membrane instead of letting all of that leak out into the rest of the blood or whatever part of the body that cell is a part of. So what will happen is these phospholipids will form a bilayer where the polar heads are pointing both to the inside and the outside of the cell. But their non-polar tails don't want to be near the water, or I should say it's energetically unfavorable for them to be in contact with water. So they will sequester themselves on the interior and form a membrane. That phospholipid bilayer is just a fundamental part of every cell and every organelle within every cell. The phospholipid bilayers can also have other cellular mechanisms embedded in them in order to transport ions or other molecules to either side of the surface. They become like these big logistical staging grounds for cells, and it's all very exciting. They also will form, I don't have a figure of it, I don't think. Your textbook actually does, but they'll form instead of a bilayer, if you have only a small number of phospholipids, then they'll form a micelle. Let me see that. I gotta see where the camera's pointed here. So phospholipids are also detergents. Laundry detergent, dish soap. I don't want to say every detergent is a phospholipid, but phospholipids make good detergents. So if you have a small concentration of the phospholipids, then they will form a micelle where the polar heads will be on the outside and all the non-polar tails will be on the inside. This is called a micelle. And so the reason why micelles make good detergents is because oftentimes when we're using a detergent, we're trying to get rid of things that aren't water soluble. If you spill salt on your shirt, that's no big deal. You can just wash it away and the water will carry it away. But if you spill oil or grease on your shirt, then water's not going to do it. And so what the detergent does is it creates this little alcove of non-polar tail groups, and your little piece of dirt or oil or whatever it may be that is soiling your clothes or your dishes will be sequestered in the interior of the micelle. But because the polar head groups are pointing outward, the micelle as a whole is water soluble, and so the water will then carry it away. It's a pretty neat process, discovered long before anyone knew anything about chemistry. Soap is kind of an ancient technology, originally made from rendered animal fat and ash from the fire. So anyway, so that's another way that phospholipids work. And I would say that these are kind of the fats that we think about. They're fats that are actually fatty. They're greasy, they're oily, and things like that. But now we're going to move on to some fats that are maybe a little bit unusual and have more nuanced purposes and roles within our biochemistry. So the first is steroids. So steroids are chemical messengers. They will sort of initiate and regulate other chemical processes in the body. And I won't go beyond that because it's not my expertise, but steroids are incredibly important and they have lots of diverse functions. But the idea is that they will regulate other chemical processes. And steroids are actually fats. They are molecules that are made up of mostly nonpolar groups, and we see here a figure with the steroid nucleus. So every steroid is going to have carbons in this configuration, and then there will be different groups here and there. Maybe there's a double bond here or a double bond there. That's what makes the different steroids. But they all share this nucleus. So if we go to the next page here, we can see cholesterol. Cholesterol is a steroid, and you see down there at the bottom it has that steroid nucleus. So there's an OH group on the left, there's that kind of a longish tail on the right, and there's a double bond and a couple little things, but you can see those 3 cyclohexanes and 1 cyclopentane that make up the steroid nucleus. So cholesterol is the fat that is sort of lining our blood vessels, and it's famous for building up when you have an unhealthy diet or lifestyle and constricting those blood vessels. But actually cholesterol is a necessary and beneficial molecule in our body. It's just when it gets sort of out of balance that it becomes a problem. So cholesterol is one steroid. Of course, there are steroid hormones, and testosterone and estrogen are they steroid hormones or are they other hormones? I better stick to what I know, and that's these 3 steroid hormones on the screen right now. So hydrocortisone and prednisone and aldosterone are all steroid hormones that provide these chemical signals that will regulate lots of different important functions in the body. And then in addition to steroid hormones, there are prostaglandin hormones. Prostaglandins also are sort of based on this template of cyclic molecules that have different groups coming off of them. And so here we have prostaglandin E2 and prostaglandin F2A, and I do not know what their function is in the body, but they're hormones, and so they're chemical signals that will regulate other chemical processes. So the prostaglandins you can recognize by having that cyclohexane and the cyclopentane next to each other, distinct from the steroids, which have 3 cyclohexanes and 1 cyclopentane group. And these are largely nonpolar molecules, and so they count as lipids. So here's just a quick overview of the different types. So triglycerides are the fats that we think of as energy storage right? That when you eat a lot during the good times and you store excess energy as fat in order to be able to live off of during the lean times, that was their biological purpose. They store energy long term in a more sort of efficient way than sugars or anything else. Okay, and then the phospholipids make up the structure of cell membranes and organelle membranes. The steroids will regulate growth, immune response, inflammation, etc. And cholesterol is responsible for the transport of fatty acids and structure of cell membranes. So cholesterol is sort of how the fatty acids get around the body to where they need to be. And then prostaglandins are also hormones. I guess these ones that we showed you regulate blood pressure, stomach acidity, inflammation, etc. And so that's it for today. That's lipids. We'll cover proteins tomorrow, and Friday nucleic acids. And nucleic acids will be kind of a big one because that'll be the whole, what's called the central dogma of biochemistry, the whole idea of how information in those nucleic acids gets translated into actual biomolecules. So today is probably the shortest day of the week, but we've got some good important topics coming up.